So, okay, just let me check that. Okay, it works. Perfect. Sorry for the technical problems. So, and thank you very much for the invitation. So today I will speak about derived equivalences for gentle and skew-gentle algebras, but using some geometric tools. So first, let me start with some motivation. So the motivation is really from representation theory, comes from tilting theory. So we start with this general problem. So we are given a finite dimensional K algebra. So here K is a field. And we want to describe all algebras B such that we have a triangular equivalence between the derived category of A and the derived category of B. And so it's a very general and difficult problem in this generality. But what tool do we have to solve this problem? We have the theorem due to Ricard, which says that if A and B are finite dimensional algebras, then they have the same derived category if and only if there exists an object T in the derived category of A with different properties. So first, they shouldn't be, so condition one, it says that you don't have extension between T and okay, I try to, no, maybe it's not a good thing to do. You don't have, you have some rigidity for T. Then you want the endomorphism algebra of T to be isomorphic to B. And you want a generating property saying that the thick subcategory of dBA generated by T is given is the entire derived category. So in other words, so a thick subcategory means the smallest triangulated subcategory stable under taking direct factors of on the okay. So such an object is called a tilting object. And so if we find some tilting, if we can, so we can, using the theorem, we can come back to the general problem. And so given a finite dimensional algebra A, we would like to describe all tilting objects in dBA. So I will explain how to solve this problem in a very simple case, which is a case where A is of type AN. So of course this is, well, this was known from years before, that the description of tilting object in the case of the path algebra of AN quiver, but I will use here some geometric tools, and these tools can be generalized in the setup of gentle and skew-gentle algebra. So this is what I want to explain, but I will treat the baby case, which is the AN case, to explain you how it works. Okay, so now I cannot go further. Okay, so I will start by defining the notion of graded arc on the disk. So this is due to Haydn, Katsarkov, and Kontsevich. So I start with a disk with n plus 1 marked points on its boundary, and I define what a graded arc on this disk is. So it's the data of two things, gamma and theta, where gamma is just a segment linking mark points, and theta is a real number such that measuring the angle between the horizontal line and gamma. So it just, you have to decide. So here I gave some examples. So you have this blue this blue arc gamma 1 with angle theta 1. So here you see that theta 1 is positive and greater than pi, between pi and 2 pi. And for instance, I draw gamma 2, the red one, with theta 2 and theta 2 here, since I go in the converse direction. So theta 2 is a negative here. It's a negative number. Okay, so this is my definition of a graded arc. And when we have a graded arcs, two graded arcs that intersect either in the interior of the disk or on a marked point, we can define the index between gamma 1 and gamma 2. And the index here will be the, so I take this is given by these angles, and this gives a kind of, so it's a natural number, and so this is the upper integral part of the number theta 1 minus theta 2. Okay, so it permits me, so so it's not the measure of the angle between the red and the blue segment, but a kind of, I mean, so here, for example, in this example, you can check that the index from the red one to the blue one, from gamma 1 to gamma 2 is equal to 2. And here I think yeah, this is, okay. I'm sorry, I think my angle is not at the right place, because it should be between gamma 1 and gamma 2, so it should be like this here. Okay, so this is my definition of graded arc. So now I give two more definitions. So I will give the definition of a full system of graded arcs on this disk. So it's a collection of pairwise non-intersecting graded arcs that contain all the sides of the n+1 gon. So, and when I say non-intersecting, I mean no intersection in the interior. So here I give two examples of full system. So I can take in this case only the sides of the n+1 gon, or I can take any partial triangulation of this polygon. I define now what a dissection is. So a dissection is a collection of pairwise non-intersecting graded arcs that cuts out the disk into polygons with exactly one boundary component. So here on the right of my picture, you can see two examples of dissection. So in the first one, I just took the n+1 gon and I removed one arc. So this is an example of a dissection. And on the second example, I started with my full system, and I removed some arcs so that each polygon have exactly one black side in their boundary. Okay, so and here yeah. So here you can, yeah, just a small remark. You can check that these two dissections, they have exactly the same number of arcs, which is a general property of dissection. So they have a fixed number of, which is exactly n, n or in this case. And so now I defined it. So here all arcs they are graded. So we have some value between corresponding to indices between these two green arcs. And I call degree zero dissection. So it's a dissection where all indices between two green arcs are zero. Okay, and so now with this, so we have these definitions, and to such either such collection of graded arcs, we will associate A infinity category. So before telling you how to do that, I want to go back and tell you a bit about A infinity categories. So of course I have no time to explain the full theory of A infinity categories in this seminar, but I just give you a few ideas so if you don't know what A infinity category is, just a few ideas of what it is. So first, a definition, which is not super precise, but just give you an idea. So A infinity category, so it's the data of some objects, some morphism. So given two objects, X and Y, I can define a home space between X and Y, and this this set of morphism between X and Y has some additional structure. It's a Z-graded vector space over the field K. And I have some higher composition. So for any n greater than 1, I have some composition mu n. And so my mu n is, so if I have given n morphism that are composable, so one morphism from x0 to x1, one morphism from x1 to x2, etc., one morphism from xn minus 1 to xn. I can compose them to apply this operation mu n of fn to f1. And this mu n of fn to f1 is a morphism from x0 to xn. And to this data, so this higher composition should satisfy many complicated relations called Stashev identities. So I don't give you this relation here in this talk, but so you have some relation that has to be satisfied. Just a few remarks now about this notion of A infinity category. So the first remark is that we can consider mu2. So mu2 is, so you are given two composable morphism, and you associate a morphism between x0 and x2. So it's like a composition, a usual composition, but it's not associative in general. So in fact, A infinity category is not a category. It's yeah. So it's not associative. However, if you assume that all your higher composition are zero except from n equal 2, then the Stashev identities tells you that exactly that mu2 is associative. So then you get a category. So it means that any category is, well, any k graded k category is a infinity category. But the converse is not true. And the third remark is that if what the Stashev identities for n equal 1 implies that, well, says that the composition of mu1 with itself is 0. So this means that if I take the home space between x and y to any object in my category together with mu1. So remember that this is a graded vector space, and mu1 has actually degree 1. So it's a complex because I have this vanishing condition that mu1 composed with itself is 0. And since it is a complex, we can define, we can compute the homology of the complex, and we can define H of A, the homology of this, the cohomology of this A infinity category. And the definition is that you take the same objects, and as a space of morphism, the space of morphism in HA between two objects X and Y is just the homology of this complex XY in A. And then this is a category, this HA mu2. So this is why we say, so in general, in an A infinity category, mu2 is not associative, but it's associative up to homotopy, which exactly means that if we take this thing, this H of A, we get a category, a usual category. Okay, so now what can we do with this this A infinity category? So there is a construction of due to Seidel that if I start with A infinity category, I can define another A infinity category, twisted of A, the category of twisted complexes over A. And it's again a infinity category. And this A infinity category contains A inside of it. It's much, much bigger, but it contains this A infinity category A. So I will just give an example a bit later so you see how it works. And the theorem due to Seidel say that, so I start with A infinity category. I perform twist of A, so it's again a infinity category. And I take the homology. So now I end up with a usual category. And this usual category is triangulated. So from an A infinity category, I can construct a triangulated category. So let me give an example, a very simple example, but that tells you a bit how the kind of construction it is, because I didn't give you the definition of twisted complex, but just to give you an idea. So if I start with a finite dimensional algebra, and I look at the category of indecomposable projective A modules. So it's a usual category, and since it's a usual category, it's a infinity category. So here I take all the other higher composition to be 0. Now, if I compute what is twisted of A, I end up with the category of bounded complexes of projective A modules, but seen as a DG category. So a DG category it's like a infinity category, but I have mu1, which is not 0, and mu2, which is not 0, but then higher mu's are all zeros. And now, if you compute the homology of this DG category, the cohomology of this DG category, you end up with the bounded homotopy category of projective A modules. And so here we obtain, so with this construction, we get the derived categories of an algebra. Okay, so now I come back to my my disk. Can I come back to my disk? Yeah. Okay, so now we'll define the topological Fukaya category of the disk. So we start with a full system of arcs, or maybe a dissection on this disk. And now I define a infinity category. And so my A infinity category is very small here because it's finite. So I have my objects, they are the arcs of S, and that's it. So I have finitely many objects. And to define the space of morphism, so if I have given two arcs, X and Y, I will have a morphism between X and Y if and only if X and Y are in such a position. So if they have a common endpoint, and that X is before Y in the in the anti-clockwise uh, direction. And now remember that X and Y are graded arcs, so I have the notion of an index between X and Y, and this index is here I denote it by P. And so then my home space between X and Y, which is be one-dimensional, and it will be in degree P, this non-zero space in degree P. So remember that the home space between two objects in A infinity category should be a graded vector space. Also, I should add some identities. So if ohm between X and X in my A infinity category is just K in degree 0. So I put some identities also between my objects. And now I have to define my compositions. So here mu1 will always be 0. And mu2 will be like the composition of angles in the following description. So if I have three arcs like this light blue, dark blue, and green. So I have one morphism from F, then one morphism G, then the composition of GF will be the angle between the light blue and the green arc. Well, with a sign, but we don't really care about the sign today. And all other mu2s are 0. Well, except also that mu2 of something with the identity will be this morphism. I mean, I want identities to behave like identities. And I may have some higher composition, and this will happen exactly when I have an enclosed polygon in my full system of arc. So if I have F1, F2 up to Fn, as in the following picture, then I will have mu n of Fn to F1, which will be the plus minus the identity of the object X, which is the codomain of the domain of F1. Okay. And now, so I have, yeah, and this defines A infinity category. And so here is the theorem due to Haydn, Katsakov, and Kontsevich that say that this AS is a infinity category first, and that if you take any two different full system of arcs or dissection, then you can, well, you have a triangle equivalence between the associated triangulated categories. And moreover, this triangulated equivalence is canonical. So as a corollary, you can speak about the Fukaya category of the disk with n+1 marked points, since you can start with any full system of arc. And so now, what happens if I apply this result with S a special dissection? So I take this dissection as in the picture here, and I take it this degree 0 dissection, and I can always find such a dissection. And now so in this example here, you can see that, well, it's a dissection. So here I don't have polygons enclosed by green arcs. So I don't have any higher multiplication. And this will imply that in this case that it's a usual category, and this category is just, so it has so here in my example it's 7 objects. It has 7 objects and just morphism from left to right that compose. So it's just the category of indecomposable projectives over the AN quiver. So as a corollary, this Fukaya category is a triangle equivalent to the boundary-derived category of the AN quiver. So here is a result I wrote a few years ago with Pierre-Guy Plamondon and Sibylle Schroll. So we proved that we have a bijection between basic tilting objects in this Fukaya category of the disk up to isomorphism. So they are in 1-to-1 correspondence with degree 0 dissection of the disk. And this permits to describe, well, first to describe all the tilting objects, and to describe also, it's easy to compute the endomorphism algebra of these tilting objects. So here is an example. So I take this dissection, which is a bit more complicated than the previous one. So I still have 7 arcs for my dissection. And I have one morphism from 1 to 2. I have one morphism from 2 to 3. But here the composition is 0 because, well, I don't have any morphism from 1 to 3 anyway. And they don't, these arcs don't intersect, don't share an endpoint. So this composition from 1 to 2 and 2 to 3 is 0. I have one morphism from 2 to 4, and here the composition 1, 2 to 2, 4 is not 0. So I get an error from 2 to 4, but the composition is not 0. And I continue like this, and I have my algebra, which is described by a quiver with relations. And this algebra is actually derived equivalent to A7 in that case. Okay. So now I will finish my talk by explain what we can do beyond this AN case, because for this AN case there is nothing really new. It was, I mean, all the tilting objects were already described. But so the thing is that what we could think about this with this geometric approach is to replace the disk by a compact oriented surface with boundary and marked points on this boundary. So if we do so, if we want to define a graded arc on this surface, and so an arc will be replaced by a curve linking, or the homotopy class of a curve linking two marked points. But we need the notion of graded arc. So we need to be able to measure angles. And here we don't have the horizontal. Horizontal doesn't mean anything for an abstract surface. So to be able to measure the angles, we will add an extra notion, which is a line field on the surface. And so this line field will play the role of the horizontal in the disk case. And then we can define the notion of a graded arc and of index between intersection of two graded arcs. so this is how it works in the very general case. And then we have this, so in fact, so this was a setup used by Haydn, Katsakov, and Kontsevich. So we have so they could prove exactly as they can define to a full system of arc and prove that this triangulated category is completely independent of the choice of the full system of arcs you started with. And they also prove, and this was also shown and well in a different way by Hopper, Plamondon, and Schroll, that this this category is actually the derived category of an algebra A, where A will be a gentle algebra. So what Hopper and Plamondon and Schroll did is that they started with a gentle algebra and they associate a surface, which is actually the surface defined by Haydn, Katsakov, and Kontsevich. Okay, and again, so what I proved with Plamondon and Schroll is well, the same theorem as before, but here now it was new. In this general setting, that we have a bijection between tilting objects and degree zero dissections. So as a corollary of this result, we get the following. We get that if we start with two gentle algebras, then they are derived equivalent if and only if the corresponding surface with line field are diffeomorphic. So it means that really, I mean, that you only need to, yeah, the derived category is encoded by the surface together with the line field. So just a few remarks about all this. So in the case of a general surface, so you have much more complications that arise in comparison with this case. In particular, you have new indecomposable objects that are not that do not correspond to arcs. So here I give you an example. So you start with a cylinder with one marked point on each boundary. So here in green, I just so here I take the horizontal line field again. And in green, I have a dissection. And then you can check that the algebra corresponding to this dissection is just the Kronecker algebra. And now you know the derived category of the Kronecker quiver, and it's much more complicated than the derived category of the AN quiver. In particular, you have tubes. You have so you have one parameter families of objects, of indecomposable objects. And here, these tubes, they correspond to arcs. So here on the left part of my picture, I draw an arc that have some self-intersections. And so these arcs correspond to an object in my derived category, which is some object. So here I have two self-intersections. So it means that it will be at floor 2 of some special tube. And I have also the bounce object that will correspond to closed curve here. Okay, so it just to tell you that in general, when this category is not so. I mean, the description of indecomposable object is complicated, much more complicated than in the AN case. So in the AN case, the indecomposable objects are just in bijection with graded arcs, and so there is no more objects. But here there are objects that will never be part of a collection of a full system. Okay. And to finish my talk, I will just say a few words about the skew-gentle algebra case. So I just give you the definition. Well, I didn't give you the definition of a gentle algebra, but you can take as a definition that these are algebras arising as a dissection of a graded surface. So now I start with a gentle algebra given by a quiver and some relations, and together with an action of the two elements group, Z2. And I assume that this action is an action of the quiver, on the quiver. So then we can define this notion of a skew group algebra, which was some notion studied in the 80s by Reiten and Ritman. So what is this algebra? So it's given by, as a vector space is just a tensor product of A by the group algebra of my group Z2. And as a product, I will just twist the the product of elements by the action. So if I have an element A G and I multiply it by A prime G prime, I will get A G of A prime tensor G G prime. So it defines me a new algebra, which I denote it by A star Z2. And by definition, this algebra is skew-gentle. So this notion was introduced by Gais and de la Peña in the 90s. So just to give you an example, I can start with a AN quiver, but now I take my orientation so that I have some symmetry. And here I take the automorphism of order 2 that fix 3 and sends 1 to 5 and 2 to 4. And now if we compute so here, well, the first thing we have to notice is that the algebra, so I started with a basic algebra, but now when I do A star Z2, it's not basic anymore. But if I look at the category of indecomposable projective over this algebra, I get the following algebra given by 1, 2, 3 plus 3 minus. So the path algebra of a quiver of type Dn, D4 in this case. So here, this vertex 1 corresponds to the projective E1 tensor the unity of my group times my skew-gentle algebra, which is isomorphic to E4 because E5, sorry, because 1 and 5 are in the same sigma orbit. But here some phenomenon occur. Here it's the fact that 3 is fixed. And since 3 is fixed by my action, if I look at this projective, so E3 tensor the unit of my group A star Z2, so it's a projective module, but this projective module is not indecomposable anymore. It decomposes into two indecomposable summons. So that's why it splits into two vertices. So I have two vertices corresponding to 3, my new quiver, 3 plus and 3 minus. So now what we did, so in a joint work with Pierre-Guy Plamondon, we tried to use this all these things about skew-gentle algebra, but we tried to do it in the A infinity and Fukaya setting. So we start now with a graded marked surface, S eta. So S is the surface and eta is a line field, and we assume that we have an automorphism of order 2 on this surface. And we also start with a full system of arcs or dissection, which is sigma invariant. And now we will associate to, we will define the Fukaya category of S over sigma eta. And so S over sigma, so in general, my sigma will have some fixed points by this action. And so S over sigma will be not a surface anymore, but an orbifold surface. And we define this Fukaya category as follows. So I start with my sigma invariant system of arc. I do the same kind of construction as before with the star Z2, so the skew group construction. So this works. But then I have to do some plus to split the idempotence in my construction. So I split the idempotence, but in the A infinity setup, it's much more complicated to split the idempotent in my category. I take twisted complexes and the H0 of this, and I get a triangulated category. And so what we could prove is that this category, I mean, using what Haydn, Kontsevich, and Katsarkov and Kontsevich did before, that this category does not depend on the choice of the full system of arc you started with. And so we proved that this category is equivalent to the derived category of skew-gentle algebras, and that we prove almost the same theorem as before, but it's not finished yet. So I mean, so we proved that we defined a generalization of the notion of dissection, but for orbifold surfaces. So we call it degree zero orbifold dissections, and we show that any such dissection give rise to a tilting object in this category. And we conjecture that the converse is true. I mean, that this is actually a bijection. So this is a work in progress. And so I will just end my talk with giving you an example of such degree zero orbifold dissection. So here I start with a disk I take a Z2 action on the disk, which is the rotation around the center of the disk, a rotation of 180 degrees. Okay, and I take this dissection, and which is clearly sigma invariant. Okay, so here I have a symmetric picture here. So here is my surface above. And now I do so I mod out S by sigma. So what do I get when I mod out S by sigma? So I could imagine that I cut along this diameter of my disk, and I just identified the point of this diameter. And what do I get? So I get this picture. So it's again topologically, it's again a disk. But here, since the center of the disk is fixed, I get a special point, which is an orbifold point here that I denoted by a red cross in the picture. And then my green dissection I started with give me this sort of generalized dissection. And I can compute the endomorphism algebra associated to this dissection, and it gives me a D5 quiver in this case. But I can also find some new dissections that do not arise as a symmetric dissection coming from the from the original surface. So for instance, I can get this kind of dissection here, which would correspond to this quiver, so which is again a D5 quiver. So we know, of course, that these two algebras are derived equivalent. But here, so I just did a reflection of one of these arrows. And so here, this quiver is not symmetric anymore, and it means that this algebra is not skew-gentle. So, of course, it was known before that skew-gentle algebras are not closed under derived equivalence. And but here, well, we conjecture that using this thing, we can find all algebras that are derived equivalent to skew-gentle algebra. And yeah, so I will stop here. Thank you very much for listening.
So thank you very much for your very nice talk. Thank you. Are there any comments or questions? So maybe I start with some questions. What do you think about the characterization of silting objects? Means geometric type of characterization of
Yes,
silting.
so in fact we did so in this collaboration with Sibylle Schroll and Pierre-Guy Plamondon, we characterize silting objects in these Fukaya categories associated with surfaces, and they are also in correspondence with dissections, but so not degree zero dissection, but for silting objects. So here we need degree zero because we don't want, for tilting, we don't want ext, non-vanishing ext.
Yeah.
So in the silting setup, you don't want positive vanishing, positive ext. So you just ask that each time you have two arcs intersecting on endpoints, the index should be negative. And then this will give you a silting object, and silting objects are in bijection with such, yeah. So in this setup, silting object, it works very well. But in the skew-gentle case, we only do with tilting because, well, we don't know what to do with silting. It's I don't know, it's much more complicated. But for the gentle case, it worked. I mean, at the origin of the project, we just wanted to characterize tilting object, but on the proof we just realized that it worked the same for silting, so we just removed the T by an S, and it was okay. So yeah.
And another question: if we work with the morphism category of projective, means in a state of the category, but morph category of the complexes was just concentrated in degree 0 and 1 of projective margins.
Oh,
I mean, not up to homotopy, just the morph category.
Oh, so you take the category, and with object are just two terms.
Yes, yeah,
complexes of projectives.
Projective, yeah. And this is exact category, not in general abelian means. But what do you think about tilting objects here? Because recently we know that there is a bijection between the tilting objects of this category and toe tilting objects of the, for example, if we start with the one-dimensional algebra, there is a bijection between toe tilting.
Yes. So I mean, so what I know is that for tilting objects, for gentle algebras, they were defined in this work by Padrol, Pilot, Plamondon, Palu, or in this. So some people did some characterization of tau tilting modules. But yeah, I cannot tell you the precise definition, but it's written somewhere. But the thing is, yeah, then I mean, here we really work with the derived category, and somehow you can sort of forget the algebra. So, and if you want to, because the set of tilting objects is something which is just depend on the whole derived category. But if you concentrate on tau tilting object, you need to know the module. Well, you need to know the algebra. It does not. It's not independent of the derived category. It's something you need to know the algebra you started with. So it's the point of view is a bit different. But I know that there are some results in this direction. So.
Thank you. So are there any questions or comments? So if not, let's thanks again. Thank you very much for your very nice talk. And
Thank you.